Hello, my name is Jonal Zabalaga and I am a PhD student at the Technical University of Munich. Today, I'll be presenting a geometric slush-free tracking method for robotic manipulators. Our motivation comes from the agile transportation of liquids. An average waiter is able to seamlessly transport multiple filled glasses and dishes while dodging the people that gets in their way. Automating these skills would be beneficial to multiple industries, especially those where the transportation of liquids plays a crucial role. Unfortunately, the agility and generality of the waiters does not transfer to existing autonomous robots. Aiming towards this goal, in this work, we propose a slush-free tracking algorithm. More specifically, we present a real-time slush-free tracking technique that solely requires the reference trajectory and the robot's kinematic constraints to output slush-free and kinematically feasible joint space commands. Before delving deeper into the details of our method, let's try to understand how is a slush-free maneuver defined. Sloshing can be prevented by suppressing lateral accelerations on the container. If we look into the literature, we observe that existing slush-free methods emulate the liquid's motion as a virtual pendulum model. This choice inherits two main drawbacks. First, its angular parameterization prevents it from being applicable to all SO3. And second, the virtual pendulum's rod length arises as an additional hyperparameter. Aiming to overcome these limitations, in this work we replace the spherical pendulum model with a virtual quadrotor, which is inherently slush-free and differentially flat. The benefits of doing so are threefold. First and foremost, a singularity-free and continuous coverage of all SO3 is guaranteed. Second, the quadrotor's differential flatness allows us to compute slush-free orientation references for any 3D trajectory without any additional computational cost. Third, the dependency on the rod length is dropped. Having motivated the choice of using a virtual quadrotor, we proceed to present the main building blocks of our methodology. The presented solution is decoupled into three stages. First, we use the quadrotor's differential flatness to compute a slush-free orientation reference. Second, we present a cascaded proportional derivative controller to track the desired reference in the task space. Third, we utilize resolved acceleration control to formulate a convex quadratic program that maps the desired task space accelerations to joint space while satisfying the robot's kinematic constraints. In the upcoming slides, we proceed to provide further details about each of these three blocks. In the first stage, we assume that the end-effector exactly tracks the geometric reference while mimicking the motions of a quadrotor. This allows us to leverage the quadrotor's differential flatness to calculate slush-free orientation references. This means that we only require the acceleration of the reference trajectory and a yaw reference, which we fix to 0, to calculate an orientation whose motions are guaranteed to be slush-free. In the second stage, we convert the slush-free reference obtained from differential flatness into task space acceleration commands. To do so, we define a post-error function in SE3. Upon this error, we apply a cascaded proportional derivative controller. In the third and final stage, we convert the task space commands into joint space. For this purpose, we formulate a quadratic program that ensures the kinematic feasibility of the obtained joint configuration. In this formulation, there are two design choices that are particularly noteworthy. First, to ensure that the QP always remains feasible, we add slack variables. These are heavily penalized in the cost function and therefore only get activated if the accelerations commanded by the task space controller are infeasible with respect to the kinematic constraints. Second, to facilitate real-time implementation, we approximate the Jacobian and the Hessian by keeping them constant. This assumption holds true when the optimization problem is solved at a high rate. For example, in the case of a Franka Emika Panda robot, the resulting QP has 27 decision variables and thus can be very efficiently solved. To assess the validity of our method, we conduct simulated and real-world experiments on a Franka Emika Panda robot. When doing so, we compare our method against a non-slosh-free variant, where the part based on the quadrotor's differential flatness is deactivated. The comparison is conducted according to four criteria: position error, average and maximum slosh-free errors, and slack variables. We generalize the evaluation by running the comparison in three different trajectories: a loop, a Lissajous trajectory, and a helix. Each of them is evaluated for different navigation times, which allows us to evaluate the performance of the presented slosh-free tracker in slow-moving as well as in agile and aggressive maneuvers. Given the similarity of the results across all three trajectories, in this presentation we exclusively focus on the Lissajous case study. First, we show an animation depicting all the slosh-free motions computed for this case study. The slowest trajectory at the upper left part relates to a trajectory of 5.25 seconds. The duration of the trajectory gradually decreases until reaching 3.75 seconds at the lower right part. The respective benchmarks are shown in the right side of the slide. Starting from the top row, we have the position tracking error, average and maximum slosh-free error values, and the slack variables, all plotted for different navigation times. Intuitively, the lower the navigation time, the more aggressive the trajectory. From these results, we observe that both methods demonstrate equivalent tracking accuracy across all navigation times. However, the slosh-free variant stands out by delivering a substantial enhancement in the elimination of sloshing. When the reference trajectory becomes excessively invisible, the slack variables adjust the space commands, ultimately leading to an increase in slosh. Having understood the behavior of the presented slosh-free tracking method, we validate our findings in a real-world robot. For this purpose, we attach a cup of water to the robotic arm's end-effector. As it is apparent from both videos, our method in the right avoids spillage successfully. For further details, please check the paper on arXiv or download the code from GitHub. Thank you very much for your attention.